Hello, we are Urban Intelligence team from Ukrainian Catholic University, and we would like to present you our smart city project named RoofMap.
Our cities grew exponentially during the last century. The growth created massive consumption of Earth's resources and affection on climate. Food production is one of the most influential industries in this case. Some companies in different countries are trying to optimize food production and delivery by building farms inside cities, especially on rooftops. Nowadays, urban agriculture is gaining momentum, and we decided to contact with a key farm organization to discover the actual problems in this area. We investigated the growth to an urban agriculture action plan for Toronto, created by Toronto Food Policy Council. They described a set of steps which were implemented to develop urban agriculture in Toronto. Along with it, they provided a scope of the next steps and problems which need to be performed in the closest future. There are several of the next steps, such as identifying rooftops, estimating an efficiency of roofs that are appropriate and potentially available for growing food. We expect that automatization the process of prediction appropriate rooftops will make urban agriculture more attractive to the businesses. I mean connection growers and suitable growing space owners. It also will help to decrease the temperature of the building and save electricity, which is used to cool rooms by conditioners. It will also reduce the amount of CO2 emitted by trucks which deliver food to end user. So it will partially solve logistic problems.
So, our solution is to collect the data that's crucial for the roof farms from open sources, analyze it, and create the model for predicting the efficiency of cities' rooftops. Let's go through the main features. The source for buildings geometry is OpenStreetMaps, and the Overpass service provides API for collecting data from it. We receive information about location, roof shape, area, and the height. Also, we are looking for the building type and the amenities inside. Some tops are not appropriate at all for the farms, such as domes, onions, and spiked roofs. On the other hand, buildings with large flat roofs are the best candidates for us. Sometimes there is no information about building features. In this case, our program estimates them by using other properties of the building. For example, we estimate the height by levels amount. Also, we are looking for the grocery shops, supermarkets, and restaurants nearby to find possible ways of consumption. This data aggregates into the logistics score for each building. Here you can see estimation of the score on the map of Toronto.
So, also, for sure, to decide the best place for city farms, we needed information about weather conditions and air quality. As a data source for air quality, we chose Breezometer API. The service provides real geodata with information about air quality with high accuracy. Analyzing air quality data for roof farms is pretty easy. The higher value of the indexes, the better is the place for the farm. As a data source for weather condition, we chose Dark Sky. Dark Sky API provides geodata about temperature, cloud cover, and humidity. Weather condition data is not so easy to analyze as an air quality index. Too high and too low cloud cover is unacceptable for roof farms. Plants need both sunlight and rainwater. Low and high values of temperature and humidity are also bad for roof plants. The high temperature in combination with low humidity makes plant dry. In another way, high humidity with low temperature makes plant rot. Ideally, day temperature must be around 20-25 degrees by Celsius and humidity must be around 70%. So we scraped geodata from APIs by 8 cities and analyzed it. Let's look at the distance to the closest shop. Distribution for all cities is right skewed, so there are very few buildings with high distance to the shop. Mean distance is about 300 meters, and considering that we have right skewed distribution, the median is more representative and it equals about 180 meters. So most of the buildings have stores at very close distance. And we have a similar distribution with the area of the buildings. The data is also right skewed. There are few buildings with a really big area of the roof. The mean area this time also doesn't give us a lot of information, as data is skewed. Median is about 200 meters. It is enough for small roof farms. Now let's look at correlation metrics of Pearson and Spearman coefficients. There is no strong correlation between coefficients, so there is no reason to research the detail of correlation.
So, we scraped data by 8 cities, and by the time we had no actually running farms, we manually label our data based on expert knowledge and efficiency of solar panels in that region, if exists. We've got numerical data and regression problem, because we want to calculate an efficiency based on our features. Then we tried a bunch of models, from linear regression to XGBoost classification by ranges of efficiency with tuning hyperparameters. We've used cross-validation to test the model's ability to predict the new data that wasn't used in estimating it. As we get more complex models and increase the number of features, we get worse metrics. So by the time we had not so much labeled data, we decided to choose lasso regression as our main model. We've created a web application prototype which provides an interface for getting information about roofs. Users select bounding box of a city area and get information about its buildings, including the efficiency score. The service runs on Flask with Python and scientific libraries such as scikit-learn, GeoPandas, NumPy for data analysis. And the front end uses Leaflet for maps. As a result of user request, we provide a heat map with buildings by predicted future efficiency of farms.
Let us see the visualization of our data from a manual. For example, let's look at this building. Our model estimates efficiency for this building equals to 8.99. It happens because of the area of this building's rooftop is very big, and the closest shop is almost inside this building. Let's compare this result to other buildings. For example, let's look at an example for this one. The area of the rooftop of selected building is very small, and the closest shop is a little bit far from this building compared with the previous one. That's why our model predicted efficiency only 5.65. As for the other features, like air quality, cloud cover, humidity, and temperature, they are pretty similar in terms of one city.
We have several directions to work on our product. First of all, we would like to improve our predictive model. Such factors as time series, rent and cost analysis, the impact of neighboring buildings' shades, and maintenance costs are first candidates to be added. Furthermore, we plan to add the recommendation system that will help future farmers to find the best places to build a roof farm. Moreover, we are expecting to provide analysis tools for farmers to give them an ability to calculate annual costs, help industry newcomers to plan their spendings. Finally, our service expected to be a platform for connecting restaurants and farmers. Cafes and restaurants will find the best suppliers nearby, while farmers will be able to find consumers for their products.
That's all for now. Thank you for your attention.